Good afternoon. My name is Adrian Durant. Here we have Miguel, Galeno, Adrian, Chavez, and Lyon. We're Team 19, and we plan on participating in NASA's CubeSat design competition. Our advisors were Dr. Tosunoglu, Dr. Tanzo, and Dr. Pradeep Shinde. So, for project description, our objective for the satellite is to be able to detect weather patterns and global environmental changes. For the satellite, we were able to implement an HD camera in order to study climate change. The NASA and Department of Defense are heavily interested in the PICO satellites that we're developing for the competition, and our constraints were to meet with the budget requirements and also the size of the satellite and not being able to interfere with other satellites up in orbit. So as you can see here, these are three pictures of our from beginning stages to our final assembly. The left shows, or my right shows the CAD drawing. The middle shows the shell of the outer and inner shells, and you can see carbon fiber. And then the final assembly is what we have recently come up with, and we'll talk about the structure.
Our biggest motivation was to improve on the work of previous near-Earth Explorer teams. They comprise of different senior teams and student-led organizations. Our biggest motivation was to be one of the first satellites to be comprised of a composite, specifically carbon fiber structure. And like you said, we're going to image topographical components. And CubeSats were started back in California Polytechnical University in 1999. They were comprised of 1U to 3U, which ours is a 3U, which is 10 centimeters by 10 centimeters by 30 centimeters. In FIU, CubeSat started in 2014. It was a student-led organization called the Near Earth Explorers Club, led by Dr. Pradeep Shinde. Two teams have gone to the NASA FunSat competition, and both times they've placed second place.
All right, so for the objectives, main objectives were to improve the internal and external structure by reducing, also introducing carbon fiber. Adrian will discuss that further in a little bit. Also to develop a mechanical gear system to rotate between the user's selected cameras from the ground station. And this group was also tasked with implementing and experimentally testing the communication system, the attitude control, the structure, and the camera system. The standards that we use, just a quick overview, everything was given us by NASA through the FunSat competition. We also had to follow FFA regulations and the FunSat guidelines.
Going on to the structural design, NASA pretty much restricts us on using composite structures as the exact structural component. What we have, this is it's an exoskeleton that's made out of aluminum. It's a hybrid between aluminum and carbon fiber. What we're trying to do is prove to NASA that these carbon fiber structures or composite structures are indeed strong enough to handle the payloads that happen when you go into space. Carbon fiber is extremely lightweight and a little bit easier to manufacture. So simulation plan, we went and did the requirement, which is 10 G's of force at the worst possible, which is 2.7 Kelvin, and with the force acting straight down on it. And then we also were planning to do a simulation for a drop test. So manufacturing process, we started with a foam mold, then gel coat with mold release, just to perfect the surface finish, and then it ended up with a hand wet layup with a vacuum bag that lasted 24 hours. That ensured the structural rigidity and then the ease of removal as well as the surface finish on the outside. Here are some visual representations of the manufacturing process. Here we have the foam with the gel coat wrapped in aluminum foil and a mold release to ensure that it's easily removed. The vacuum bagging. Throughout this whole process, I wore proper PPE. It was in a controlled environment, glasses, gloves, and breathing apparatus. I've worked plenty with composite structures before, so those are important to look for. And then finally, for the testing. With the help of Edgar Polo in the civil department, we were able to use the compression tester. These satellites will basically, when launching, receive forces heading in a unilateral direction. So what we chose was a benchmark of 10 Gs, which is a requirement, and it far exceeded the expectation and went all the way up to 25 Gs. So that further proved that we really should be using these composite structures because it is a whole lot lighter than the aluminum, and stronger as well.
And now we're going to speak about attitude control. So what exactly is attitude control? Attitude control is how the satellite is controlled in space. When the satellite is deployed into space, essentially, it's thrown into space, so it's tumbling all over. That's when the attitude control really comes into effect, and it helps stabilize the attitude when it reaches space. For our design, we used copper wire. I'll speak about the design later on. The actual attitude control is made up of two separate subcomponents: attitude determination and attitude control. The attitude determination is necessary to be able to locate the orientation and position of the satellite in space at any given time. This is going to be made possible through the LSM-9DS0 sensor board and some sensors that will be placed inside the satellite. Now about attitude control. The key component of attitude control is the magnetic torquers. The magnetic torquers consist of a magnetic material usually wrapped in copper wire. This will create a magnetic field when voltage is applied because it is a solenoid type coil. With the interaction of Earth's magnetic field with the created magnetic field, it will create a torque, which is what's necessary to rotate the satellite in space. For our design, we chose perm alloy as our core material in 2.86 millimeter radius with 9 centimeters in length, and we chose a 36-stage copper wire. Based on our calculations, we were supposed to create a 500 microtesla magnetic field. With testing, I got 600 microteslas. The difference there, it's usually caused by Earth's magnetic field, since the testing wasn't done in a Helmholtz coil, which is what eliminates Earth's magnetic field while we're still here.
Okay, so for the optical system, this top right picture shows the design that we finished with the senior one, and the bottom one is what we finished up with in the end of this semester and what we actually implemented. We were able to reduce the overall weight and also material. Before, everything was made from stainless steel or other type of metal, and now everything is ABC plastic, so it drastically reduced the weight. We were able to keep the same amount of strength, and due to the low loads that we're using and the low mass, the plastic worked fine. And it also made for very easy assembly. So we were able to, although we increased the diameter of the gears, we reduced the thickness, and we also increased the amount of teeth. Again, it still reduced the overall weight. So each gear is 28 millimeters in diameter and has a 2 millimeter bore, which fits perfectly on the stepper motor shaft. So this bracket attaches to the inside of the carbon fiber, and the gears are just pressed fitted onto the shafts. And basically, this stepper motor will rotate the platform to the desired camera, which is the goal of the overall system, is to be able to rotate between the thermal camera, the HD camera, and an image sensor. And again, this is all chosen by the user who is located on the ground. The stepper motor is 5 volts. It only needs 1.3 watts to power. Some important facts about it is that it has 48 steps per revolution and less than 0.002 horsepower. So this is what we use as parameters for all the AGMA calculations. And most importantly up here, you can see the safety factor is well within reason, and the forces, which I'll get into in a second on the simulations, they all went as planned. And the stepper motor itself is capable of 41 revolutions per minute. So the left is just one gear being simulated as if it was being the contact stress between the teeth, just to make sure it wouldn't fail. That's based off just a little bit less than the maximum that was calculated using AGMA. The middle shows the von Mises and the deflection of the platform. Basically, we just simulated that as if each camera was acting the weight on vertically downward on top of the platform, about 0.2 newtons. And then most importantly was the beam. So we modeled it as a cantilever beam, and the whole assembly fits into this hole and that hole, the both shafts, and that whole force acting down is about 1 newton. So everything was very minimal, the deflection was very small, and the stresses were very small. So now to the actual assembly. Again, you can see the ABC plastic gear, the bracket, the small stepper motor, the microcontrollers, the picket, which we use to program the microcontrollers, and then this is the one camera that we ended up testing at this point in the phase. And then the bottom left over there just shows the breadboard being connected to test the stepping motor. So for actual testing, we started out with testing the deflection of the bracket, as you can see it in the top left. The weight that's on that is far greater than anything this bracket will see, but we just wanted to see how much it's going to deflect while it's up there. It passed fine. The deflection is 0.0002 millimeters. I mean, it's very, very small. And then the most important testing that we did was to determine and confirm the number of turns that it requires for the stepper to rotate each camera 45 degrees. So each camera is placed at 45 degrees apart, and we were able to confirm by testing it from reference points that it takes exactly 6 steps for the motor to rotate each camera to its correct position. So this made the programming much easier and allowed us to get everything positioned perfectly.
Okay, now onto the communication subsystem. This is pretty groundbreaking work because the previous teams didn't really have a form of communication. The purpose for this was to not lose contact with the satellite once it's in orbit, and we also want to send and receive messages to the satellite. We want the satellite to send and receive messages from the ground station, from us. So the way that we did this is we used LabVIEW to program the radios, the USRP 2920. I'll show you in the later slide. And from our work, we were able to send text, pictures, and videos. And for now, we were able to send save videos and text and pictures. So we couldn't figure out how to save the videos. Next slide. Over here, you see the setup that we were working with throughout the whole semester. On the left, you have on the top, you see the transmitters and the receivers, and they work both ways. They can send and receive. Over here, you see here's the windows for the transceiver, and here's for the receiver. Here you have a more close-up view of the USRP 2920. And at first, they were connected through EMO cables, but then we were able to connect them to antennas, which is what we wanted ideally, because you can't have a really long EMO cable in space. And then you have the power and the Ethernet cables. Next slide. So over here was our outcome, and then from the hours of programming, we were able, here you can see the text. So at like 7:51 with 45 seconds, we were able to send communication subsystem, and then at 7:51 with 45 seconds, it received communication subsystem. The same thing at 7:51, hello world, it also received the hello world, and we get the last FIU CubeSat Simulator presentation, the same thing, it received it at the same exact time. Next slide. For the pictures, for now we were sending sample pictures from the desktops. And as you can see here, we clicked on the lighthouse, and then after we clicked the control key, it was able to receive the picture of the lighthouse. Last. So here is, although this is a snapshot, this is actually me and another partner, Yanni Rodriguez. We were working on the videos, and we're connected to the webcam. And then, as you can see, on the receiving side, it has some text, and then on the other side, you have the images of us working together. So that was it for the communication.
So this slide just shows some of the testing that we were able to do with the full assembly. I'm not going to show the video on the left. It just basically shows us, and it's the same thing it's doing right now. It's reading temperatures of this room and transmitting it to the computer. There's a temperature sensor that's connected to the beagle bone down there, which is blinking in blue, and it just spits off temperature readings as we go. The last two videos are just showing the camera rotating. So this first one shows it rotating facing upward, and it's going to rotate back. And then bottom video shows the camera facing downward, which is how it will be in space if you can think about it that way.
So yeah, the assembly now is wrong side up. The bottom is actually this part right here. But for the camera working, we don't want to just take a picture of the table.
The goal of design, as we mentioned earlier, the main purpose of this whole satellite was to study climate change patterns and weather patterns and make that free public data available to everybody. It's going to be powered by solar cells. Everything's been made from readily available materials, which makes it very low cost, low environmental problems. And eventually we would like to be able to communicate with multiple languages. Right now it's just C# and English, that's it.
This is our Gantt chart. As you see, we're proceeding time, so presenting our
Alright, so for the most important, which is the future work for the club, they were able to receive a grant from NASA to go up into space using one of the launch pods. So as the innovations keep coming, the competition in 2018 will allow them to actually launch the satellite, the 3U and the 1U up for the competition. And then we want to actually get published, we want to get our senior design paper published for being the only team, the first and only team to use composite structure, specifically carbon fiber. There's only one other team in the world that's doing it, and they're so far in the design phase, and that's the CubeSat.org. They're sponsored by them, and that's pretty much it for the future work. Is just to keep the club going with this prototype. Thank you very much.
Questions?
What was your biggest challenge in creating this?
Getting everything to work together. And luckily, you guys saw the 1U team present before us, so we were able to work with them. And obviously, our advisor, Dr. Shinde, helped us out quite a bit. But there's just so many subsystems that are involved in a satellite that it's impossible for one or even two teams to complete everything in a senior 1 to senior 2 semester. I mean, this is why, Adrian said this club started in 2014. In reality, a lot of this stuff that's on the satellite, not shown here, but a lot of the design and the calculations has been going on for over a decade. So the hardest thing was just really trying to implement everything and actually produce something now that the future teams can really work off of and have a good basis. For example, the next rendition of the senior groups, they're working on cooling systems. Like right now, that camera is running, it gets hot, so they're working on the cooling systems for that, and also not changing the way that the optical system is mounted, but actually creating a structure for it and containing it. So again, the biggest challenge was just trying to get everything together and make sure that we can leave the next groups with a really good foundation to kind of, to launch this. It's going to launch in 2 years, so they have something to build up.
I would have to say the hardest part was the programming. It's easy to say that we built the composite structure because we're mechanicals. That's what we do. We work with materials, but then we got to actually code it and make it work. It's definitely a bunch of sleepless nights getting on the computer. So that's definitely the hardest part.
Okay, great. Thank you.
My first question to you is, you mentioned your composite structure performed better than you initially thought, and it was sufficient. Why did you include if it was sufficient, why the aluminum frame?
So, the beginning of this senior, we wanted to implement just the inner structure that would allow us to remove all of the inner components while keeping the external structure to try to stay within the regulations that NASA has set forth. But through the testing and things like that, we realized that we should probably put it on the next team to just create a completely composite structure out of carbon fiber and tell NASA and kind of demonstrate to NASA that it is really worth going for. One of the other key components to this would be an autoclave to test the vacuum chamber, because there is such a phenomenon called degassing that happens within the layers of the carbon fiber that can cause catastrophic failure if it did happen to get to the components. We do want to try to prevent that from happening, but as of right now, the autoclave that's on hand isn't working, as well as the vibration tester just doesn't reach the frequency that we need it to. So from the structural standpoint, it does give us what we need, which is the 25 G's of load, and it can go past that. It didn't deform at all or break, and so yeah, that pushes the envelope a little bit.
How did you account for line mismatching or areas of enriched epoxy? Those are all detrimental to your structure.
I've had a little bit of experience working with carbon fiber before. I worked on the Formula SAE team and we created the body out of it. Through just years of practice, we've known that epoxy resin is the resin that kind of stays laminated throughout the whole thing and creates that structural rigidity and flexibility that we need without delaminating the layers. The way I made sure that the resin kind of seeped through the whole thing, I had peel ply and a mesh throughout the whole thing to kind of ensure that it's spread evenly. Throughout the hand layup, I squeegeed it through and then vacuum bagged it. Obviously, there's going to be manufacturing errors here and there, but if we do have the proper components, such as an autoclave and a full vacuum bag, a full vacuum chamber, we can definitely see better components made.
One last question. Did you use SIs to calculate everything you mentioned, millimeters at some point, or did you use both units?
We use both. With the simulation plans and things, at least for mine, I used SI because the NASA components are all 10 centimeters. When we had to go to the compression testing, which is at FIU, is in America, we had to use standard units and kind of go back and forth between the two.
How did you ensure that no mistakes were made? We've seen it before with companies like NASA. You use both units and something usually gets missed.
The proper insurance probably wasn't there, it was just gone on faith. But definitely as we progress, we're definitely gonna keep both in line for insurance.
Do it twice. Do it twice. That's the end. Don't say faith. I don't trust your faith. You know, I just say we're gonna calculate it twice. We're gonna run the numbers again. If it matches, then you are at least satisfied that the first numbers, you have some confidence in those results.
Thank you. Any other questions?
Just one comment. When you cite the industrial standard, you should cite the standard number, not just vaguely say NASA standard.
Okay. Honestly, in the previous presentation we had done that and we were a little bit over time, so it was one of the areas that we felt we could cut out. But agreed, we should have the specific standards that we related to.
And what's the temperature range? Just like for experience in space. Is plastic material adequate for that temperature range?
So yeah, the plastic material is adequate. The melting point of the ABC is about 120 degrees Celsius. The stepper motor won't reach anything near that, and neither will the motherboard for the camera. What will affect it is when it's on the dark side of the moon and when it's in the sun, which I believe you had more specific. You had a temperature that you were using for that.
Yeah, the dark side of the moon would give us 2.7 Kelvin, and when it's directly radiated to the sun, we would have the aerogel, which kind of protects all the components from the interior, and that's what the carbon fiber structure rounded with the aerogel would give.
But that low temperature where the plastic fragile and lose those strengths.
Thank you. Can you say it again? I'm sorry, I didn't hear you.
Yeah. At that low temperature at the dark side,
Yep.
it's a few Kelvin, and where the plastic loses strength, mechanical strength, and become fragile.
Well, the astrogel, the aerogel, sorry. I mean, the ratings that we've had have been based off the previous team, so ultimately we should test them just to confirm their data is correct. But going off the decade or more of data that we've received from previous PUNSAT groups, we felt confident to still use it. But in the end, ultimately we should test it in a very extreme condition just to be certain. Because I mean, once it's up there, if something goes wrong, mission over. So.
Look at the operating temperature of your material. That's really one of the first steps you can do.
Yeah.
You have the temperature. You should have that data for the plastics that you use. See if you lose your material strength when it reaches that temperature, or what happens to the material. His concern is
It's brittle.
get brittle.
Yeah.
And